Okay, so basically, before the Big Bang, things get a little tricky language-wise. If you define the Big Bang as that crazy hot, dense moment, cool, we can roll with that. But our best guess is that there was something before that, called inflation. What was before the Big Bang? This has always bugged scientists, but now they may have figured it out. It freaked them out, though, as Brian Cox said, something not good existed way back when. The idea is that the universe was kind of just chilling, cold and empty, but expanding super fast. Then, this expansion slowed down and stopped. That energy that was driving the expansion then got dumped into space, heated it up, and bam, made all the particles we're made of. That's what we call the Big Bang. So what was there before the Big Bang that scared scientists? Let's find out. This theory has an extension called eternal inflation, which is basically inflation going on forever, but stopping in little spots. Imagine the universe's fabric stretching and stretching, then slowing down in patches. Each one of those patches is like its own Big Bang and universe, ours included. So, you end up with this wild idea of a fractal universe with endless Big Bangs, the inflationary multiverse. In space, pure nothingness is more of a thought experiment than reality. Even if you zapped away all the energy, it wouldn't be truly empty. Right now, our universe is packed with stuff, regular matter, radiation, antimatter, neutrinos, dark matter, dark energy, and so on. Without energy, the universe still makes new energy. It's like the universe doesn't get our idea of total emptiness. If we removed all energy leaving a void, you'd think it would hit absolute zero, but not. Even in an empty universe, its expansion would still make radiation. This goes way into the future, and even back to before the hot Big Bang. The universe, it looks like, never really gets empty. So, could the universe have come from nothing? We can say for sure that something is always around. Even if you take away all the particles, antiparticles, photons, and quanta, empty space is still there. Get rid of any mass or energy sources, clear the space of electric, magnetic, and gravity fields, and keep photons and gravity waves out, and you still have a kind of emptiness. Quantum fields are still kicking around in that space, and the basic constants and physics laws are still in play. There's a finite amount of energy there in that space. That's as close to nothing as we get in our universe. Even if you can think of a more nothing state, it's not real. No experiment can make it. Following science, we know something always exists because true nothing can't be. But the why is still a mystery. Right now, our universe is far from empty. It's bursting with stars, gas, dust, galaxies, quasars, cosmic rays, and radiation left over from the Big Bang. With better tools, we might find more signals we think are out there, stuff like gravity waves or signals from dark matter, and a better sense of black holes. Aside from the super bright stuff, everything we see is in a universe that's always changing. It's cool to get how our universe changes on a huge scale. Space and time are both expanding, meaning if you put 2 points far apart, the distance between them, the time it takes light to travel between them, and the light's wavelength, they all increase over time. Basically, the universe isn't just getting bigger, it's getting colder. As it grows, light stretches to longer wavelengths, lower energies, and cooler temps. The universe was hotter before and will get colder as time goes on. During all this, stuff with mass or energy pulls together, making clusters and a giant cosmic web. If you could somehow remove everything, matter, radiation, energy, the thing you'd have is empty space, still expanding, still following physics laws, and still full of quantum fields. That's as close to nothing as you get, but it's still following rules. Taking anything else away would make it unrealistic, not like the universe we know. It seems like dark energy would still be there, even in a universe without matter. Basically, if every quantum field was at its lowest energy state, we'd be at the zero-point energy of space, where you couldn't get any more energy for work. In a universe with dark energy, a cosmological constant, or the zero-point energy of quantum fields, it makes sense that the zero-point energy wouldn't be truly zero. As the universe keeps growing and cooling, radiation will become powerful, beating out matter, and dark energy will be the main player. But there was a time in the past, not the future, when something else was calling the shots besides matter and radiation. During cosmic inflation, before the hot Big Bang, the universe expanded super fast and constantly. Instead of matter and radiation running things, it was the energy of inflation itself, like today's dark energy, but stronger and expanding way quicker. If eternal inflation is right, but time is limited, where did the universe come from? There must have been a beginning, right? To answer that, let's break down three mashed together ideas. 1. The hot Big Bang in our universe. 2. Cosmic inflation and how it set the stage for the Big Bang. 3. The question of an ultimate beginning and why inflation and the original Big Bang idea might not fully answer it. In the early 1900s, four things came together. Alexander Friedman showed with Einstein's relativity that a universe filled with matter and energy can't sit still, it has to expand or contract. How fast it does that depends on how much energy is in space. Henrietta Leavitt linked the brightness changes of stars to their actual brightness. Vesto Slipher saw that galaxies were moving away from us really fast. Edwin Hubble and Milton Humason found similar stars and galaxies to those Leavitt found, figured out how far away the galaxies were, and confirmed they were outside of our own. All this led to the idea of an expanding universe. If the universe is expanding, space is stretching, making matter less dense. Light stretches too, which cools the universe. If you rewind, matter and radiation get squeezed, making the universe denser and hotter. Rewind even further, and everything gets crammed into one point with infinite density and temperature. That's the initial idea of the Big Bang. This resulted in 5 key expectations on the early universe's hot and dense beginnings, which are the following. 1. The universe should be expanding. 2. In the beginning, the universe ought to have been relatively homogeneous. 3. The universe was so hot that stable neutral atoms can't form, preventing the cosmic microwave background from developing. 4. Nuclei also couldn't form stably, causing the creation of light elements, such as hydrogen, helium, etc. 5. The universe was so hot that neutrinos played a big role in the way that the universe was ran back then. So, could the universe have started from nothing? Probably not, because there's always something there. Physicists believe empty space still has quantum fields and stuff, with a tiny bit of energy called zero-point energy. You can't really get rid of that. Our universe is definitely not empty now. It's packed with stars, galaxies, gas, and all sorts of radiation. We might even find more hidden signals with better equipment, like gravitational waves or clues about dark matter. Everything we see is changing. Space itself is expanding, so things are getting farther apart, wavelengths get longer, and the universe cools down. But mass and energy still clump together, making big structures. If you could take away absolutely everything, you'd still have space that's expanding and following the laws of physics. That's the closest we get to nothing. Even in that case, dark energy would still be around. If all the quantum fields had the lowest energy possible, that's zero-point energy. But since we have dark energy, that zero-point energy might not actually be zero. The universe will keep expanding and cooling, and eventually, dark energy will be the main thing around. Before the Big Bang, there was inflation. Space expanded super fast because of something like dark energy, but way stronger. If eternal inflation is real, the universe must have had some kind of start. To understand it better, let's look at 3 things: the hot Big Bang, cosmic inflation, and whether the universe had a beginning. In the early 1900s, scientists like Alexander Friedman and Edwin Hubble made some big discoveries. Friedman realized the universe can't be still, it has to be expanding or shrinking. Hubble saw that galaxies are moving away from us really fast. This led to the idea that the universe is expanding, which means it used to be smaller, hotter, and denser. If you go back far enough, everything would be squeezed into one tiny point. That was the initial Big Bang theory. From that idea, scientists made 5 predictions. The universe should be expanding. It should have started out pretty uniform. It used to be hotter. It should have made light elements like hydrogen and helium. It should have had a lot of neutrinos. These predictions have been proven right, so the Big Bang Theory has been the main explanation for the early universe since the 1960s. But over time, some problems came up with the Big Bang Theory alone. It couldn't explain a few things like why the universe has the same temperature everywhere, why the universe seems so flat, why we don't see certain leftover particles. Instead of just accepting those problems, scientists tried to find a solution. In the 1980s, Alan Guth came up with the idea of inflation. He said that the universe went through a phase of superfast expansion early on. This inflation idea could solve those problems. Everything has the same temperature because it used to be connected. The universe looks flat because inflation stretched it out so much. We don't see leftover particles because inflation kept the universe from getting too hot. Inflation theory also made predictions about the structure of the universe that have been proven right.